explaining physics in heels. Today's lesson with Professor Diva, algebra-based physics, and today's lecture is units and vectors. In today's lesson, we're gonna look at the basic tools that we utilize when doing physics. In physics, when we deal with a number, for example, 5, we don't deal with just the number like saying there's 5, but we always add a unit to it. This unit specifies what property of a body we are referring to. Since we are talking about meters, then of course we are talking about length. But sometimes we need even more information than this, right? If I say 5 meters, where are we talking about 5 meters? 5 meters at sea level, 5 meters on a mountain, 5 meters to the right, 5 meters to the left. We need more information. This number with a unit without any other accompanying information is called a scalar. If I add more information to it and I specify the location and the direction of these meters, then I turn a scalar into a vector. So a vector will be 5 meters to the right. What is a vector made of? It is made of course, the numerical value, the unit, never forget your units, and finally, the direction. Is there a way for us to represent vectors in a simpler form than always saying 5 meters to the right? What if I don't have pages and pages of writing available? Yes, there's a very simpler way to write a vector using the beauty of an arrow. Now, in physics, the first step to working with vectors is establishing an origin. The origin is the point where we take all measurements to be 0. Think about it. Your birth is the origin of your life. So your age at your birth was 0. So you always measure your age according to how much time has passed since your birth. Every measurement requires an origin. When we deal with vectors or arrows, we always have to pick an origin, so a point, and then we have to draw an imaginary line going through that point. I'm gonna assume that my vectors go to the right normally. Everything that is in the direction that I picked originally when I established my origin, we take this to be the positive direction. Everything to the left of that will of course be the negative direction. So now it's pretty simple. If I denote this line, this direction by x, if I write my position will be 5 meters in the positive x direction. How do we represent this vector? Very simply. First of all, we look at the direction. What is our direction? Positive x direction. As I said, our line is x. Positive is in the direction of my initial arrow to the right. So I know that my position will start from the origin and will go to the right. Secondly, I look at my unit. In this case, it is 1 meter. I need to specify that in my drawing, 1 meter will be this length right here. So from the origin, I start and go to the right, the number of units according to my numerical value, which is 5. So I'm gonna go 1, 2, 3, 4, 5. So this point right here is where my arrow will stop. This right here of 5 units is of course my position vector. We did it! We drew our first vector. Now to show why it is very important to show direction, what if I gave you a different position and I told you draw R2 to be 5 meters. Notice how it's the same number of units, however, to the negative x side. In this case, what do we start with? We start with the direction. The direction is negative x side, so I need to go to the left, contrary to my initial arrow. I need to go then still meters, so I'm using the same unit, and 5 to the left. So I'm gonna go 1, 2, 3, 4, 5. So this is the point where I'm gonna draw my new arrow that is my vector R2. As you can tell, R and R2 have the same number of units in them, but in opposite directions. So if we didn't specify the direction, we would have lost some very important and vital information about our system. Direction is key. I gotta say, I just looked over the footage and I realized that my shirt was a bit too unbuttoned for my own taste, so I apologize for that. I guess you got a freebie. But coming back to our lesson, since vectors are so incredibly useful, and since physics utilizes mathematics to be objective, can we come up with a mathematics of vectors? We absolutely can. And that's called vector operations. Just like regular numbers, we can add vectors, we can subtract them, we can decompose them, and we can multiply them. So let's talk about it. First of all, let me make a very important distinction. When I write r, for example, this is a scalar. When I put an arrow on top of it, it becomes a vector. So if you're wondering what this funky arrow on top of things is, it specifies the fact that we are dealing with vectors explicitly. So we need not only a number, which is a scalar, but also a direction. Now, the first operation we're going to talk about is vector addition. If I have a vector v1 and a vector v2, how can I add two vectors? It's very easy. It's all geometry. What we do is we start from an origin. Remember, always said your origin. We draw the first vector, which is v1, and then on top of the head of v1, we start drawing vector 2. So I take v2 and I put it starting from the top of vector 1. So this is v1, this will be v2. So then what's the sum? The sum is nothing more than tracing our origin to the final point where we end up. This yellow arrow right here, that is v1 plus v2 vectorially. Pretty cool, huh? It's all geometry. If I have a vector v1 to the right, fully to the right, and I have a vector v2 fully up, in that case, if I were to add those two vectors, I would need to move v2 on top of the head of v1. So I would redraw v2. What would be then v1 plus v2? It would be tracing from the origin all the way to the final point, an arrow. This is v1 plus v2. Fun fact, addition works in reverse too. If I start with a vector that I want to call r, for example, right? What I can do is I can decompose r onto two dimensions, dimension 1 and dimension 2, according to the laws of geometry. So, if I have an angle theta right here, and the length of my vector is going to be r, notice how I didn't put an arrow in order to signify the length of my vector, not the vector itself, just the magnitude or the scalar, then in this case, I can decompose my vector onto the two dimensions. If you remember from geometry, the cosine of our angle theta will be the distance or the length closest to the angle, meaning the one on the bottom, divided by the hypotenuse. This distance right here will be the magnitude of v1, and then the hypotenuse, of course, is r. Now, what's the sine of my angle? Sine of theta, of course, will be the length opposite to the angle, so the one farthest from the angle. So this distance right here, which is, of course, v2 divided by the hypotenuse, which is r. If we rearrange the terms, we see that v1 will be r cosine of theta, and v2 will be r sine of theta. So we did it. We expressed our original big vector in terms of two dimensions that are perpendicular to one another according to the laws of geometry, using cosine and sine. If it helps, let's label our axes a bit more usefully. Let's call this axis x, and let's call this axis y. If we look at it, the x component of our vector deals with cosine, while a y vector deals with sine. You're going to see this in physics all over again. It is very important to remember. When I have a vector, I denote an angle with respect to the x direction, then the x component will be the cosine. Cosine always embraces the closest length to the angle. Before we move on, here's a quick sine and cosine test. If I have my two axes right here, x and y, and I denote an angle right here, theta, where is the cosine going to be? Is it going to be on the x-axis or on the y-axis? Let's think about it. This is my angle. What is the length closest to my angle that touches the angle? It is right here, which means that the cosine will be on this side that touches my angle. Which axis is that? That is the y-axis. So in this case, the y component will have the cosine of my angle. And the x component will have which component? Sine of theta. So be careful. Cosine always touches the angle. Sine is farthest away from the angle. Now, for our third operation, if I have a vector v1, the question is, what would 2v1 look like? Well, it's nothing but addition, right? If this is v1, what I need to do is I need to add another v1 to it, because 2v1 can be written as v1 plus v1. So I do nothing but add yet another v1 on top of it. What is this? This will be 2v1. So what do we see right here? We see a multiplication of a vector with a scalar. The scalar being the number 2 in this case. Let's have some fun with this. What if instead of 2v1, I wanted to express minus v1? Could I do it? Of course. Minus v1 would imply that I have to go in the reverse order of my vector. So if this is v1, from this point, I have to draw v1. However, I flip it 180 degrees. So this right here, to the opposite side, this arrow will be minus v1. I think you can guess what vector subtraction is in this case. If I write v1 minus v2 and never forget the arrows, this is nothing but v1 plus minus v2. So the way that we represent vector subtraction, take these two vectors. I take v1, I then flip v2, so this will be minus v2, and then I put it on top of the head of v2. So that is v1, that is minus v2, and then the end result from the origin all the way up, this will be v1 minus v2. We covered a lot of ground very quickly. Way to go! Are all the vector operations you're gonna need in this class. Thank you so much for watching. Your support means the world to me. If you want more physics, be sure to subscribe and to hit that bell icon so you can be one of the first people notified when I upload a new lecture on a really fascinating topic. And if you want to get to know me better, check out my Instagram, Physicist in Heels, where I post reels daily. Well, see you next time.